Most systems we consider are actually not isolated, but they're in thermal contact with a heat reservoir. So, for example, the environment, if you consider any object that is in thermal contact with the environment will act as a heat reservoir. So, this question of system in contact with a heat reservoir is one of the most common cases we should consider in thermodynamics. So let's say that we have a system A that is in thermal contact with a heat reservoir, a system A prime. And as you can see, the way I have shown it here, system A is much smaller than system A prime. That is to say, the number of degrees of freedom for system A is much less than the number of degrees of freedom of system A prime. In other words, system A is much smaller than system A prime. For example, if you put a copper bar in a lake, right? So system A can be a copper bar and system A prime can be a lake, right? So we put a copper bar inside a lake. The lake will act as a heat reservoir. It will set the temperature of the copper bar. Now I'm going to call omega prime the number of accessible states to system A prime, the heat reservoir, the lake. So that is at energy E prime. So let's remember, this is the number of accessible states, and this is for the system to system A prime for an energy with energy in the range E prime to E prime plus delta E. And remember, delta E is a macroscopically small energy interval where we have almost no change in the number of accessible states as the energy is increasing by an amount delta E, but it is still much greater than the discreteness of the energy levels in the quantum sense. Okay, so that energy is still considered a continuous variable. So A plus A prime, A star, the total system, this one is isolated. It's an isolated system. And so that when we have system A in a state with energy E sub r, so basically I'm saying that system A, my copper bar, is in let's emphasize the fact that we're talking about a non-degenerate state, in a non-degenerate state R, and the meaning of non-degenerate is basically there is only one state that corresponds to an energy with energy E sub r. Okay, so if I say that the system A has energy E sub r, then I know that it is in a state R. So that's what it means. So since we have the total system is isolated, E sub r, the energy of system A, so let's say that this is in state R, plus the energy of the heat reservoir must be equal to the total energy of the isolated system A star. So I will have the energy of the heat reservoir equal to E star minus E sub r. So since the number of accessible states to system A prime is a function of E prime, then basically I can say that I have omega prime, the number of accessible states for an energy E prime, which is the number of accessible states for an energy E star minus ER. This is actually equal to the number of states accessible to the total isolated system when the system A has energy E sub R. Why? Because the number of accessible states to the total system is the number of accessible states to system A, but system A is in state R. There is only one accessible state, and system A prime has omega prime E star minus ER, which means the total number of accessible states to A star when A is in state R will be 1 times omega prime E star minus ER. So let me emphasize that. The number of accessible states to the total system when A is in state R, okay, the total number of accessible states to the combined system A star, this is going to be the number of states accessible to A. Well, the A is in a given state, so it is 1, multiplied by the number of accessible states to system A prime when it has energy E star minus ER. So that will be the case. Then I can talk about what is the probability P sub R of A being in state R. Okay, so we can ask this question. What is the probability P sub R of system A being in state R? The answer will be given by our statistical postulate, the postulate of equal a priori probabilities. So remember, it's the ratio of the number of states that corresponds to the scenario you're talking about divided by the total number of states that gives you the probability of that scenario. So this probability, the answer will be so A must be in state R, so there's only one accessible state. A prime must be in with energy E star minus ER, so there will be so many accessible states for the energy E star minus ER, divided by all possible scenarios for the total system where I have the system A can be in any energy in the interval 0 to E star. So all possible accessible states to the total system. So this will be basically, because all the possible accessible states to the total system A star is just going to be a number. So this is going to be just proportional to the number of accessible states to the heat reservoir, the lake, at energy E star minus ER. So this is the answer given to me by our postulate of equal a priori probabilities. So let me note here, this is due to postulate of equal a priori probabilities. So each accessible state has the same probability, 1 over omega star for the total system accessible states. So I just count the total number of accessible states for a scenario and divide it by the number of accessible states to the system A star. That gives me the probability of that scenario. Now remember that the number of degrees of freedom for system A is much less than A prime. It is much smaller system than A prime. So since I have the number of degrees of freedom for system A much less than that of A prime, small system A, the contribution to the total energy in the star system A star, because simply I have a very few particles, the energy, total energy I have for system A, E sub r, will be really much less than the total energy that I will measure in the system. So I can say that E star will be more or less equal to E prime, because this energy in the very small system E sub r is considerably negligible. Okay? So in order to calculate this probability of A having a state R, I need to look at this probability P sub R, and because it's such a sharp dependence on the energy, we remember that we look at the natural logarithm. So natural logarithm of omega prime E prime, which is natural logarithm of omega prime E star minus ER. I'm going to look at this in the limit E prime is equal to E star. Okay, or you can say that E sub r is approximately 0. It's negligibly small. So first you evaluate this function, natural logarithm of omega prime. E prime must be equal to E star. That's the first term. And then comes the second term, plus the derivative, natural logarithm of omega prime with respect to E prime. And then we have E prime minus E star. Okay, so since I have E prime is equal to E star minus ER, E prime minus E star is equal to minus ER. Okay, so this is going to become then natural logarithm of omega prime evaluated at E star minus derivative of natural logarithm of omega prime with respect to E prime evaluated at E prime equals E star multiplied by E sub r. Okay, so this part, natural logarithm of omega prime with respect to E prime, that derivative is by definition beta prime. So omega prime E star minus beta prime E sub r, the energy that system A must have. So this is these are the first two terms. I don't consider the next terms in this expansion. Taylor series expansion is what I'm doing here. Again, Taylor series expansion. And therefore, I find that omega prime, so this is basically equal to that. So omega prime E star minus E sub r is approximately equal to omega prime. So if you take the exponential, you will get omega prime E star e to the minus beta prime E sub r. So it's exponential to natural logarithm omega minus beta prime ER, exponential and natural logarithm basically disappear. So it just gives me omega prime E star multiplied by exponential minus beta prime ER. Now at equilibrium, we're going to have the same temperature. Temperature for system A and system A prime will be the same, and therefore the beta values will be the same. So omega prime E star is just a number. So for the in the scenario that omega A prime has the full energy E star, A has no energy, what is the number of accessible states? That is just a number, a constant, so that the probability that I'm after is basically just this number C times e to the minus beta E sub r. So that is going to be my final answer. The probability of system A having an energy E sub r corresponding to the single state R, that is, it is a non-degenerate state. In this scenario, this probability is a constant times e to the minus beta E sub r, where beta is, remember, 1 over kT. Boltzmann constant times absolute temperature of that system. So I want to check if this result makes sense. So according to this result, if E sub r is very large, the probability should be very low, right? So let's check that this is going to make sense. So let's see if system A is in a state with high energy, E sub r, right? And we have E prime, then is going to be E star minus E sub r. If E sub r is high, is going to be low. So E prime will be low. So this is the scenario I'm looking at. And the number of accessible states for the prime system. So basically I want to use this equal a priori probabilities to find out what this probability should be. The number of accessible states when the system A prime has energy E prime, where E prime is low, since this varies with energy as E prime minus E0 prime to the F prime, where F prime is the number of degrees of freedom for system A prime. When E prime is low, E prime close to E0 will give me very low number of accessible states. So when E prime is low, it's close to E0 prime. It's going to be, when it is exactly equal to E0 prime, it's going to be just 1. Well, I mean, it's going to be just one state exactly, right? So it's going to be reduced substantially, given that you have the energy very, very low. Then if you look at the probability, then probability of having an energy R, which was given by omega prime E prime divided by omega star total. The other one, A, is in a given state, so it is 1. So this will be very low. And on the other hand, I have probability C times e to the minus beta ER. When ER is much, much greater than KT, probability PR will be very low as well. So this is consistent with what I see for the behavior of the probability. The second important point here is that the exponential factor that we see in this distribution, the exponential factor e to the minus beta ER is called the Boltzmann factor. And the distribution we have obtained, probability for the system A having an energy E sub R, C times the Boltzmann factor e to the minus beta ER, where C is a constant. This distribution, probability distribution, is called the canonical distribution. Canonical distribution. And when we form an ensemble of such systems in order to find the probability, so an ensemble of small systems, they have to be similar systems, in contact with a heat reservoir will give us a canonical ensemble. So this is at a known temperature T. So it's like putting many copper bars into the lake. This is going to be forming a canonical ensemble. Now, continuing with this distribution has to be normalized. So if you count all possible states of system A and their probabilities, they should add up to 1. So that is our normalization condition. Therefore, we find that C times sum over R e to the minus beta ER, where R goes through all possible states of system A, this has to be equal to 1. So this constant C we're talking about is 1 over sum over all possible states e to the minus beta E sub R. Then we can basically write for the probability, we can rewrite this probability of small system A having a state R with energy E sub R in contact with a thermal reservoir at temperature T is e to the minus beta E sub R sum over all possible states e to the minus beta E sub R. So this is our, again, canonical distribution. And so if we're looking at any parameter of system A, so for any system parameter so for system A of A, we can find its average value by looking at the mean value. By definition, it's the probability of having a state R corresponding parameter value y sub R. For all possible states, we will add these up, weighted by the probabilities. So this will give me sum over R e to the minus beta E sub R the corresponding parameter value for state R divided by sum over all possible states e to the minus beta e sub R. So that's how I calculate the mean value using the statistical definition of mean value and the canonical distribution. So this is again sum over all possible states R, all possible states. Now there is an important remark here, and that has to do with the degenerate case. So what if I find that the state that I'm talking about is degenerate? So degenerate case, which is very likely. So that means there are many states, not just one state, corresponding to this energy E sub R. Okay, so for that case, I need to consider the probability of the state of having an energy E has to be a summation over the probabilities of having P sub R for all of those values that give me the same energy. So let me clarify what I mean by that. So I have the system A has a probability P sub R of being in one particular state R of energy E sub R. So P sub R is probability of having system A in state R with energy E sub R. So just as we discussed now. And now I want to know what is the probability of having the system A, probability of having system A with energy E to E plus delta E, so that the number of accessible states corresponding to this energy doesn't change. So and this omega E, the number of accessible states to system A, is not equal to 1, so it is greater than 1. So I'm looking at the degenerate case. In that case, basically the probability of all states, so this E sub R is in the range E to E plus delta E. Basically, I have to consider the number of accessible states for all of those energies in this interval where the number of accessible states is basically not changing. The P sub R values will be the same. So P sub R values will be the same for all accessible states in this interval. So basically I will find in that case the probability of having an energy E to E plus delta E is going to be a constant times the number of states that have this energy E, accessible states, multiplied by E to the minus beta E. So I just have to consider how many accessible states have this energy E and multiply the Boltzmann factor with it to get the canonical distribution. So once again, this is number of accessible states for energy E to E plus delta E energies. Okay, so that I have no change in the number of accessible states. Delta E is a macroscopically small value. Now, what is this going to give me for the most probable energy of the system? So let me finish this discussion by looking at this. So I remind myself the number of accessible states E varies with energy as E minus E0 to the power F, rapidly increasing function of energy, because this F is of the order of Avogadro's number, remember, so it's a very big number. And then I have the second factor, Boltzmann factor, e to the minus beta E. This is a rapidly decreasing function of energy. So if you multiply the number of accessible states for energy interval E to E plus delta E with the Boltzmann factor using the canonical distribution, you will find that you should see once again a very sharp peak, and this sharp peak will occur at E tilde, which is the mean value of energy for system A, and it's going to have a width delta E, and consistent with our previous discussion, the width of this distribution will be proportional to 1 over square root f. So the canonical distribution basically gives me the same result that we have considered previously. For system A is to have a sharp maximum probability for a particular energy with almost no fluctuations around its most probable value, which is the mean value of the energy. So let's summarize what we said. Well, I've considered two cases for a system in contact with a heat reservoir, canonical distribution, a non-degenerate case and a degenerate case. So system A is much smaller than system A prime. The heat reservoir sets the temperature for system A. A small amount of heat transfer in between A and A prime basically does not affect the temperature of system A prime. It's a heat reservoir. The number of accessible states to A prime for energy in the range E prime to E prime delta E is omega prime at energy E prime. The total system A plus A prime is isolated, and the corresponding the energy E sub r to the state R of system A is rather small compared to the total energy in the system E star, because system A is much smaller. The contribution from the number of particles in system A to total energy is relatively small. So you can consider the number of accessible states to A prime, omega prime of E prime, to be mostly omega prime at E star. So we can look at the Taylor's expansion around E sub r is equal to 0 to find out how the number of accessible states should be determined. And the question I ask is, what is the probability of having system A in this particular state R? The answer is the total number of accessible states to system A star with this scenario. So A must be in one particular state R, and A prime must be in several states, accessible states, with energies E star minus ER divided by the total number of accessible states to system A star for all possible scenarios. That gives me that the probability depends on the number of accessible states to A prime. This is due to the postulate of equal a priori probabilities. Since A is much less than A prime, omega prime of E prime can be expanded using Taylor series expansion For natural logarithm of omega prime e prime is natural logarithm of omega prime e star, so I set er to 0, and then the derivative, which gives me beta prime multiplied by minus er. So I find that the probability is a constant, where this constant is number of accessible states to A prime for the full energy E star, multiplied by e to the minus beta er, where I have also noted beta must be equal to beta prime because I have thermal equilibrium. And then I checked if that makes sense. If A is in a very high energy, this probability distribution tells me that the probability of having this scenario is very low. If A has very high energy, then A prime has very low energy. The number of accessible states to A prime is very low. The probability omega prime divided by omega star total will be very low. So that's consistent. The exponential factor e to the minus beta er is called Boltzmann factor. The distribution that we obtain is canonical distribution. And to statistically evaluate these probabilities, if you form an ensemble of such small similar systems in thermal contact with the heat reservoir, you get a canonical ensemble. As with all probability distributions, this probability distribution should be normalized. It should be equal to 1 for all possible states, and that gives me that this C factor is 1 over sum over all possible states, the Boltzmann factor. So that is the canonical distribution, e to the minus beta er divided by sum over r all possible states, e to the minus beta er. Beta is 1 over kT, temperature is constant because we're in contact with the heat reservoir, and E sub r is the energy of system A, corresponding to the scenario that system A is in the non-degenerate state R. For any particular system parameter, I have to consider all possible states, their probabilities multiplied with the corresponding value of the parameter. So that gives me sum over r e to the minus beta er Boltzmann factor y sub r divided by sum over r e to the minus beta er, which we will recognize as partition function later on. For the most general case, degenerate case, if you have more than one state that corresponds to the energy E, so if you are looking at an energy interval E to E plus delta E, and there are number of accessible states, omega is a function of E for those, then you have to multiply your Boltzmann factor with the number of accessible states in order to get the correct probability value. So the generalized version of the probability distribution is C times omega of e to the minus beta E, where we take into account the degeneracy for the energy E. And finally, multiplying the number of accessible states, which has a rapidly increasing functional dependence on energy, with a rapidly decreasing function exponentially to the minus beta E, I see that this distribution should really give me a sharp peak with a mean value that has a small fluctuation, delta E, which varies as 1 over square root f, as we discussed in our previous video.